Okay, so in this lecture, we'll be talking about eigenvalues and eigenvectors. So previously, we were thinking about the action of a matrix A on a vector x, okay? And we were thinking about A being an m by n matrix. So what it did was map Rn into Rm, potentially, if m and n are different, right? If A is a non-square matrix. Okay. Now we're going to focus on square matrices, n by n matrices. Okay. And they have the nice property that if x is in Rn, if I multiply A by x, it stays in Rn. Okay. It stays in the same space. Okay. So in that situation, we can do more analysis on it. Okay. So let's think about x in Rn and think about its span, which is a line through the origin like this. Okay. And let's say we multiply x by a. So since ax lands in the same space, we can potentially draw it on the same picture. So where could ax be? Well, it depends on a, right? It could send x anywhere, right? It could send it here, could send it here, could send it way off, right? But it could send it to the span of x, okay? So here's an instance of that. So again, this is my x, and if the red vector is ax, we see that acting on x, a keeps x inside of its span. Okay, and that's a special case. Okay, so if ax is inside the span of x, that means what? That means that ax equals lambda x for some number lambda, right? So remember, the span of x is all multiples of x. So if ax is in the span, it has to be of this form. Okay, and such x's that are non-zero, that have this property, are called eigenvectors. Okay, and the scalar lambda that's attached to them is called an eigenvalue. Okay, so eigenvectors don't leave their span when you multiply them by a. Okay, so that's one way of classifying it. Okay, so the only effect that multiplying by a has on x is it scales it by some number. Okay, but it stays within its own span. Okay, so the word eigen means self or same in German, right? So as to mean that x stays within its own span. Okay. Okay, so here's the formal definition of eigenvector and eigenvalue from the book. So you can read through this and see it's what I described above. Okay, so how can you determine if a given vex is an eigenvector of A or not? Okay, so this is actually pretty easy to do. Okay, so all you have to do is compute ax and see if ax is a scalar multiple of x, right? That's what defines an eigenvector. Okay, so here's an example. Okay, if we let A be this matrix and let u and v be those vectors, are they eigenvectors of A? Okay, so there's a procedure. You multiply A times u. Okay, I look at A times u and I compare it to u and ask, is there a number I can multiply u by which will give me A times u? Okay, And if you inspect it, there is, right? U times -4 will equal AU. Okay. So we write it like this: -4 times U equals AU. Okay. In other words, AU equals -4U. And that means that U is an eigenvector of A, and the corresponding eigenvalue is -4. Okay. So what about V? Okay. If I compute A times V, okay, I get this vector. And then I can I can compare V to AV, and I try to think, is there a way to multiply something times V to get AV? And there isn't, right? You can just tell by the ratio between the coordinates. Okay, so this does not equal a scalar times V. So V is not an eigenvector of A. Okay, so that's pretty straightforward. Okay, so let's state this theorem. Okay, we already mentioned it as part of the invertible matrix theorem. It's important enough to state on its own. Okay, so a matrix is invertible if and only if 0 is not an eigenvalue of A. Okay, so why is that true? If 0 is an eigenvalue of A, that means there's a non-zero x such that AX equals 0. Okay, so that means there's a non-zero x in the null space. Okay, so if the null space is not equal to just the 0 vector, okay, so there are non-trivial x's that satisfy this, which is true if 0 is an eigenvalue, then the other parts of the invertible matrix theorem tell me that that means A is not invertible. Okay, so if there's any non-trivial x that kills this, or A times x is 0, that means your null space is not trivial. That means your nullity is greater than 1 or greater than 0. And all those things mean you're not invertible by the big invertible matrix theorem. Okay? Okay, so let's discuss the procedure for finding all the eigenvalues of A. Okay, so remember, we're looking for numbers lambda, okay, such that AX equals lambda x. Well, x has to be non-zero. Okay, so we can rearrange this equation, bring the lambda x over to the left side, and then we have an x on the right side of both of these terms, so we can factor out on the right side an x like this. Okay, and the reason we add an identity times lambda is because we don't want lambda just sitting on its own. Okay, so really there is an identity here, but when it's being multiplied by something else, we omit it. But when lambda is on its own like this, we like to explicitly write the identity. Okay, so this matrix is just lambdas along the diagonal and zeros elsewhere. Okay, so notice what we have here. This is a homogeneous equation now, right? We have some matrix times x equals the 0 vector. Okay, so we know a bit about homogeneous equations from lecture 5. It says that if the homogeneous equation is going to have non-zero solutions, we require that this matrix has dependent columns. A theorem we stated in lecture 5. Now, by the invertible matrix theorem, it says if you have dependent columns, then you're not invertible. Okay, so the condition that lambda is an eigenvalue and x is its non-zero eigenvector requires that this matrix here be not invertible. Okay? Usually we're looking for invertible matrices. Usually that's a good property. In this case, we want this to be not invertible. That will confirm that lambda is an eigenvalue and x's will be the eigenvectors. Okay. So we want to check for what lambdas is this matrix not invertible. That's what we want. And for those lambdas, those will be the eigenvalues. Okay, and the check to see if this is invertible or not, we're going to use the determinant. Okay, so here's the theorem. Let A be a square n by n matrix. Okay, so the number lambda is an eigenvalue of A if and only if it's a solution to the characteristic equation of A. And that is this expression here. Okay, we form the matrix A minus lambda times the identity. Okay, and then we take the determinant of that matrix. Okay, so the determinant is usually a number, but since we have an unknown lambda here, what the determinant becomes is a polynomial, and it's going to be in degree n. Okay, so the highest power is lambda to the power n, and the lambdas will be the unknown. Okay, the lambdas will be the variable that you have to solve for. So this will be a polynomial, and you're looking for the roots of the polynomial. Okay, so you have to factor it or use the quadratic formula or something like that. Okay, so that's how you find all the lambdas, all the eigenvalues. Okay, so now I'm going to mention a property associated to each eigenvalue called its algebraic multiplicity. Okay, so the number of times lambda I shows up as a root in the characteristic equation is called the algebraic multiplicity of that lambda. And we denote it by am lambda I. Okay, so let's just see what that means by an example. Okay, so let's suppose A is some matrix and we compute its characteristic equation to be this. Okay, so we're looking for the roots of this equation. Those will be our eigenvalues. And so what lambdas when we plug into this will make this 0? Well, it'll be 5, and it'll be 2, and it will be, it'll be -1, right? That's the typo here. It should be -1. But that's not the point. The point is, what are the algebraic multiplicities? Okay, well, there's just one factor of 5 here, so the algebraic multiplicity of 5 is 1. There are 2 factors of, or corresponding to 2 here. So the algebraic multiplicity of 2 is 2. And there are 3 factors corresponding to -1 here. So its algebraic multiplicity is 3. Okay? So another fact is we can tell the size of the matrix just by its characteristic equation. Okay, so if we were to expand all this out, we would get lambda to the power of 6 as the highest lambda power, right? So that means this equation has degree 6, and that means A must have been a 6 by 6 matrix. Okay? Okay. So I'll state this theorem here. Okay? So if A is a triangular matrix, then its eigenvalues are actually really easy to find. Okay? So triangular means upper triangular, lower, or diagonal. Okay? It's just the entries along its diagonal. Okay? So you can just read them off easily. Okay? And this fact can be checked just by taking or computing the characteristic equation of a triangular matrix, and it should be straightforward to show this. Okay, so we know how to find all the eigenvalues. How do we find their eigenvectors? Okay, so suppose we know all the eigenvalues. Okay, so if lambda I is an eigenvalue, then the eigenvectors corresponding to this lambda are the non-zero x's satisfying this homogeneous equation. That's what we derived before. Okay, so notice that this is a matrix times x equal to 0. In other words, we're finding the null space of a matrix, right? The eigenvectors are the null space of this matrix, right? So we know that null spaces form subspaces, okay? And we know how to compute the basis of those null spaces, okay? So what this is saying is that all the eigenvectors corresponding to a particular lambda form a subspace in Rn. Okay, so you don't just get one eigenvector by doing this, you get an entire subspace of eigenvectors. Okay, okay, so we'll give a name and a notation to this subspace now. Okay, so if lambda I is an eigenvalue of A, then the solution set to this homogeneous equation, okay, is a subspace of Rn called the eigenspace of lambda I. Okay, and I don't think there's standard notation for this, but I'm just going to use EIG and then lambda I. So this we're going to consider to be a subspace. Okay. Now, we know how to compute the basis of a null space, so we know how to compute the basis of the eigenspace. Okay? And the basis of each eigenspace, we're going to give a special name called the eigenbasis for that eigenspace. Okay. So, as we know from computing null spaces, they can be of different dimensions, of course. So the number of basis elements you get out of the null space computation is how big the dimension of the space is. Okay? And it's the same for eigenspaces. Okay? And we give that dimension a name because it's important. Okay? So the geometric multiplicity of an eigenvalue, and I'm going to call it GM of lambda I, is the dimension of the eigenspace of lambda I. Okay, so now we have two different types of multiplicity attached to each eigenvalue. Okay, so the geometric multiplicity of an eigenvalue equal to the dimension of the eigenspace, which of course is equal to the number of vectors in the eigenbasis. Okay, and that's equal to the number of free variables you get when solving for this equation, for this homogeneous system. Okay. And now we'll mention a very important fact, is that eigenbases from different eigenspaces are always linearly independent. Okay, so let's say I have three different eigenvalues. Okay, so I compute a basis for each one. Okay, if I put all those basis vectors together, that set is linearly independent. Okay, and we're going to use that fact immediately.